All right, so one of the things that I don't think this book does well is talk about gas stoichiometry. And particularly, one of the things that they kind of gloss over are volume relationships.
Oh, is that adding them? Adding volume?
Kind of.
Like, on the quiz, we have to name which law is which.
No, I will never ask you about the names. I'm going to ask you to apply them. They don't ask that on the exam either. They just give you a bunch of data and say, here, make something with these numbers. Right? All right, so here, you want me to turn down the light? It's glossed over in the book. So volume relationships are glossed over in the book. And, yeah, you could. And they're going to ask you things like this. So here's a sample problem. So they might ask you, how many liters of ammonia can be made from 0.75 liters of nitrogen and unlimited hydrogen? And they tell you to assume conditions that don't change. So assume that things are at STP. Well, how would we tackle something like this?
Go for the legs.
Yeah, you would go for the legs. You would. How come? Okay. No, you were right on the right track, Jasmine. So you said do a fence post. Why? How many numbers do you have in the prompt? One. So the first thing you say is, I got to do a fence post. And then you want to do what? You can convert it. You want to convert that to moles. All right. Well, what do you have available that lets you to convert to moles? What's that?
22.4.
I'm not going there yet. I'm not going there yet. I haven't done that yet. Jonathan. Ooh, I like that better. Don't you have to write the reaction first? Okay. N2 plus H2 yields what?
NH3.
NH3. And if you look at that equation, it's wrong. I need a 2 and a 3. Okay. Are you happier now? Okay. All right. What now? I'm not going there. She's right. You have to figure out how to change this to moles. Well, how do we get moles? What formula do we use if someone's asking me for moles? No, what's for formula? That's not a formula. What formula do you use if you're talking about a gas and someone's asking for moles? Ideal gas law. So you could use the ideal gas law, right, and solve for moles. So moles is PV over RT. What's the pressure? Did they tell me the pressure?
No.
They did right here in these three letters.
STP.
What's STP? Pressure of 1 atmosphere. Do I know the volume? Yeah, they told me it was 0.75 liters of nitrogen, right? So we're basically going to calculate moles of nitrogen. Do I know R? I do. It's 0.0821. Do I know T? What's T at STP? 273 Kelvin. All right, so I could put these numbers into the ideal gas law and figure out the moles of nitrogen, right? So 0.75 divided by 0.0821 divided by 273. So there are 0.033 moles of nitrogen, right? And so now we could do what Jasmine was suggesting, which is do a fence post. Then now let's go from moles of nitrogen to moles of ammonia, right? And how do I go from moles of nitrogen to moles of ammonia? Shush. I'm trying to make a point. How do I go from moles of nitrogen to moles of ammonia? Give me a second, Don. The mole ratio. All right, so the mole ratio is that for every 1 mole of N2, there are 2 moles of ammonia. All right, so that ends up being 0.066 moles of ammonia. But did they want moles of ammonia? No, what do they want? They wanted liters. And how do you go from liters to moles? You could go back to the ideal gas law again, right? You know what N is now. You have to figure out what V is. So V is equal to nRT over P. N is 0.066. R is 0.0821. T, it's at STP again. Y'all scooch this up. So that would be 273, and then it's at STP, so it's 1 atmosphere. All right, and I could calculate all that out. It would give me the volume. But some of you guys aren't happy with what I'm doing. Connor in particular, he hasn't shut up for the last... So I got 1.5 liters. So he's not happy. Jonathan's got his hand up. Josh has his hand up. You guys aren't happy with me right now, right?
Okay.
Why not? Because that's a lot of work, right? Yeah, it's a ton of work. Josh, are you going to add? What are you going to complain about? That's what you're going to say? See, I got ESP. I can read your minds.
What's ESP? Epilepsy?
Oh, Connor, shush. All right, so anyways. That's a lot of work. It's convoluted. And it's completely unnecessary. All right? Because there's a couple of other ways to tackle this problem, but you have to know a little bit about gas stoichiometry. All right, number 1. At STP. What do we know, Connor? Give it to me finally.
What?
1 mole of any gas has a volume 22.4 liters, equal to 22.4 liters. Okay? Any gas, doesn't matter what the gas, what the identity of the gas is. If you have a mole of it, it's 22.4 liters. All right, so if you go back to the question, they ask you, you could do this, right? So they tell you that you have 0.75 liters of nitrogen. You know, if you wanted to go straight into a fence post, you could say 22.4 liters of nitrogen has 1 mole of nitrogen in it. Liter cancels out with liter. And they want you to change this to liters of ammonia. Right? And so then in the next step, you could do the mole ratio. Right? For every 1 mole of nitrogen, there are 2 moles of ammonia. Right? Moles cancels out. And then they want the answer back in liters. So 1 mole of ammonia, and it's still at STP, those conditions haven't changed, has a volume of 22.4 liters of ammonia. So mole cancels out with mole. The 22.4 cancels out with 22.4. And so then it's just a matter of, elaborating the fence post. All right? And so the answer that you would get for this is 0.75 times 2, or 1.5. Are you happier now?
Why is all those numbers now?
Because they all can. Are you happier now?
Why do all those
Are you happier now?
Why do all those
Answer my question.
I don't understand why those numbers.
Because it's a fence post. It's dimensional analysis.
But why do the numbers?
Because 22.4 in the numerator, 22.4 in the denominator. That simplifies.
Oh, I got you.
Okay, all right. Are you happier now?
I feel unchanged.
You feel you've changed?
I feel unchanged.
Unchanged. I'm still not happy with this. Is there an easier way, Jonathan?
Look in the back of the book.
Shush. Say what? You have a question?
Yeah.
Give me your question.
So, when you use 273, can you do it in discretion based upon the
Yes. Yes.
And then,
Yes. They have to be ideally behaving under those conditions. Okay, stop. What do you want?
You just multiply by the mole ratio.
Shush. Yeah, exactly. That's what I'm saying.
Is
that what you're going to tell me to do? Yeah, you. Okay. All right. So
only if it's the same temperatures and pressures.
Bingo. All right. So
What's his name though?
the first way I showed you was completely ridiculous and convoluted. It used the ideal gas law. This second way was a little bit better because you have this piece of information about gases at STP. There's an even better way of doing this, all right? And it has to do with volume relationships that are kind of described in a balanced chemical equation that the book, again, doesn't do justice. All right, so if you look at the equation, what did these coefficients mean way back when we first learned about them?
Moles.
They mean moles. So 1 mole of nitrogen plus 3 moles of hydrogen makes 2 moles of ammonia. But when it comes to gases, they also mean volumes. They do. 1 liter of nitrogen with 3 liters of hydrogen makes 2 liters of ammonia. And it's true, provided the conditions don't change during the course of an experiment. So this is provided temp and pressure are constant. Yes, sir. Yeah.
Yeah, but isn't this like only ideal because most reactions they create energy?
Yes. Yeah. So this is all in theory on paper because you're right. Some of these reactions are going to release energy. That energy is going to be absorbed by the particles. You're going to have greater kinetic energy. It's going to throw off your pressure. If you have systems in place that will control the temperature for you, that will control the pressure for you, then these calculations work out. All right. So knowing this makes this math even simpler. Okay? All right. So how would we do this problem if I know that particular fact? Okay. So let's go back. So what you could do is you could do a fence post starting with our given 0.75 liters of nitrogen, solving it for liters of ammonia. Instead of using a mole ratio, which you can use now as a volume ratio, all right? So what would the unit be in the denominator? Liters of N2. And what would we put on top? Liters of NH3. What is the mathematical relationship according to the equation? For every 2 liters of NH3, we require 1 liter of ammonia, or nitrogen, I'm sorry. So then again, it's just a matter of multiplying 0.75 times 2, and you come up with an answer of 1.5, just like we did when we were using that 22.4 conversion that Connor was yelling at me for 10 minutes.
If it's less than 10.
Right? We got the exact same answer, 1 piece of a fence post rather than 4. Okay? And it was the same exact answer that we derived doing the ideal gas law, fence post, ideal gas law. All right? So these are little tidbits of information that aren't quite spelled out in your book that I want to make sure that you understand. So these are extra conversion factors you can use to help you out. All right? Okay. So I want to do a couple more stoichiometry questions with you. All right? Let's see if we find some in the book.
Answers are with A,
2.
No.
Connor, relax, dude. Okay, so what I want to do is on page 409, and it's sample exercise 10.9. All right? Because now we're going to talk about conditions that aren't exactly STP or conditions that actually change as the reaction goes on. All right? So sample problem 10.9 says that I have, it talks about safety airbags in automobiles. They like this reaction with nitrogen gas, where nitrogen gas is produced from sodium azide. So they say that this bag is inflated by nitrogen gas generated by the rapid decomposition of sodium azide. We had a question in the homework like this before, right? It says if an airbag has a volume of 36 liters and is to be filled with nitrogen gas at a pressure of 1.5 atmospheres and a temperature of 26 degrees Celsius, how many grams of sodium azide have to be decomposed? All right, so let's kind of put things together that we've learned so far. So, is it a stoichiometry question? Are they asking me about one substance in an equation and then making me change it to a different substance in the equation? The answer is yes. Jonathan, what's the first thing you need for a stoichiometry question? No. A balanced equation, right? Okay, they gave it to me. All right, so the balanced equation is that you have 2NaN3 And the 2ANN3 yields 2Na plus 3N2. So I start by writing the equation, and then the next thing that I do is I go through the word problem, and underneath the substance that they're giving me information for, I write down all the data they give me for that substance. No, let's just write down what they give me, and then maybe underneath that substance, if we can figure out what kind of calculation to do to get moles. Because ultimately, that's really what you want to do. That's the first step, is try to get moles out of something. All right, so what do they tell me here? The airbag it occupies 36 liters. They're talking about nitrogen, right? They want the nitrogen itself to have a pressure of 1.15 atmospheres. So underneath nitrogen, I'm going to write 1.15 atmospheres. The temperature of this nitrogen is 26 degrees Celsius, 26.0. All right. I want you, when you write down temperatures, you see, I'm guilty of this too. When I first wrote it down, I just wrote 26, but in the book it said 26.0. Be careful. You want to write down numbers in your problems the way you see them in text. Don't change them. All right? What else do they tell me? That you want 36 liters of this. And what do they want? They want grams of this sodium azide. So this is the question that we have to do. Right? So this is all the information that they give me in that question, kind of summarized underneath the reaction. So I have a bunch of numbers, all relating to one substance. So what kind of a stoic question is this? Ideal or limiting reactant? Ideal. All right? I don't have to do a Rice chart. If it was a limiting reactant question, I'd have to do a Rice chart. I don't in this case. What do I want to achieve with these numbers? What unit do I really want out of these numbers? I want moles, right? That's the driving force for every last math problem that you and I are going to do from now to the end of the year, is moles. How do I get moles out of that? PV equals nRT. So that's the first thing I'm going to do. I'm going to use PV equals nRT. I'm going to write it underneath nitrogen just to remind you that it refers to that particular compound. All right, so moles is N. N is PV over RT. The pressure is in the right unit, so it's just a matter of substituting it into the formula. The volume also is in the correct unit. R is a number you memorize. Temperature, however, is all wrong. So we have to add, and in this case, we can add the decimal places. All right? All right, two significant figures, correct? So this is 1.7 moles of nitrogen, because all these numbers were referring specifically to that one substance. Okay, now that I have moles of nitrogen, can I convert it to moles of sodium azide? How so? You do a fence post. You say 1.7 moles nitrogen. There are, let's see, 3 moles nitrogen for every 2 moles sodium azide. Did they want my answer in moles? How do they want them? Grams. So how do I convert back to grams? What's the molar mass for sodium azide? 14 times 3. What's sodium? I can't read that. Yeah, 22.9. 64.9, is that the mass? No. Is it? Yeah. 64.9 grams. So moles cancels out with moles, and then I would just basically take 1.7 times 2 times 64.9, divide that by 3. I get 74 grams of sodium azide. Okay? Any questions? What's your question, Don? Oh, not yet? I won't be in the room. You can ask questions of the proctor all you want. Huh? I'm not allowed to talk to you for 48 hours.
48 hours? Like before or after?
After. burning.
Wait, so what do we do when we come to your...
You don't?
What?
I probably will take those 2 days off.
You just did...
No.
Then it'll be so quiet.
No, you won't come back the next day. You probably have another exam to take. Emma.
Oh.
Yeah.
How do you know which one to use?
Oh, you look at the word problem. Okay.
Like, write it down.
Boil. If you see, you know how Boyle's law is PV equals PV? If they give you 2 pressures in a volume, or 2 volumes in a pressure, use Boyle's law. Yeah, basically. No, you don't have to know them by name. Chances are, and I have to look at the reference sheet, they don't have them separated out as Boyle's, Charles, and Gay-Lussac. I believe the only thing on the reference sheet, grab me a reference sheet, is the combined gas law. Hey, no, they're over here. Emma, you gonna ask them something else?
So, is that for the Gay-Lussac one? Like, so we technically, do we have to know them?
You don't know them by name.
Okay.
Okay, let me see what's on here. Oh, this is what they gave you for gases. Do you see Boyle's, Charles, Gay-Lussac are combined anywhere on there? No. What do they give you? I'm not there yet. I was asking for the first one that you see there. The ideal gas law. Oh, boy. Are we up the creek without a paddle? They didn't give me Boyle, they didn't give me Charles, they didn't give me Gay-Lussac, they didn't give me combined. Do I have to memorize them all? No. Why not?
Yeah, it's just easy.
You just cancel one letter out of it.
Can we derive them? We sure can. All right, so for instance, let me show you how to derive these things. Okay, so say for instance I've got PV equals nRT. All right? Remember all these equations are reflexives? What if we're only focusing on pressure and volume? Let's get rid of everything that's not P or V from that equation. All right? Make that reflexive. PV equals PV. Okay, there's Boyle's law. All right, next. PV equals nRT. Say, hey, these are rhetorical questions. Rhetorical means you put your hand up. All right. Volume and temperature. What if I was just focusing on volume and temperature? I had a question that gave me 2 volumes and a temperature. Cross everything out. What would you have to do to get both of those variables to the left of the equal sign? Divide by T. Make it reflexive. V over T equals V over T. That's Charles's law. All right? Next one. What if a word problem gave me volume and, what was it? P and T. Pressure and temperature. 2 pressures in 1 temperature or 2 temperatures in 1 pressure. And that's all I wanted to focus on was pressure and temperature. How do you get both of those variables to the left? Divide by P by T. Okay, make it reflexive. P over T equals P over T. That's Gay-Lussac's law. All right, last one. What if I had a question that had 2 pressures, 2 volumes, and a temperature, or 2 volumes, 2 temperatures, and a pressure? You had 5 numbers in that word problem, and you needed the combined gas law, but the reference sheet didn't have the combined gas law on it. That's harder than just looking at this. Take this equation and get rid of everything that isn't those 3 variables, P, V, or T. How do you get all those variables to the left of the equal sign? Divide by T. PV over T. Make it reflexive. PV over T equals PV over T. The stuff on the left are your initial. The stuff on the right is your final. So you don't really have to memorize it. You can derive them all from ideal gas. Yes, Connor?
Can't you just remember that T goes on the bottom?
That would be helpful.
And then you just like skip all of that stuff.
That's great. You could. But you could derive it all algebraically.
Please no.
Jonathan? Oh, you are still hung on this real versus ideal. Can you let me get to it by the end of the week? Okay, all these equations work under ideal systems. If you have a real gas that is sticky, because it's slightly polar, you have to put correction factors to these. They're called van der Waals factors. So all these things really only work for ideal situations. We have like a perfectly non-polar substance. They're in the book. I want you to assume, it's under the assumption, gases that are real, you can force them to behave ideally by making them hot. Okay? Lowering the pressure on them. Any condition that you study those real gases that would normally be sticky, any condition that you give them where you allow them to be away from each other and separated, makes them behave more ideally. You can manipulate the lab's conditions to make them behave ideally. Okay? Yes, sir.
In case people don't get frosting it out, that'll make you think of things. Because you can take it over, the PV over T equals some constant. So P1, P1, P1 equals a constant. And separately, P2, T2 equals the same constant.
You can set them equal to each other that way too. All right. Let's look at something else. So I'm going to keep gas stoichiometry questions in the book really straightforward. I don't think I'm going to give you limiting reactant questions. That would just be mean. But you can do limiting reactant type things with this. So if they had given me initial quantities of sodium and initial quantities of nitrogen, you would have figured out how to use the ideal gas law to convert them to moles, and then you use a Rice chart the way we did in the past. Okay? I'm not going to do it to you because it's just very labor intensive, and that goes beyond the scope of what you're going to see on the test. But know how to do this. Okay, we're just trying to put some concepts together, tie them together. All right, the next thing that we need to talk about is some further applications of the ideal gas law, and these are some notes that I want you to write down. This is 10.5 in your book. 10.5 is called Further Applications of the Ideal Gas Equation. And what you're going to be asked to do in this next section is to use the ideal gas law to calculate M. Capital M, and I try to write it in like a kind of frilly way, cursive, so that you don't confuse it with capital M for molarity. So this is where things get really ugly. All right? The reason why things get ugly is chemists, in their lack of wisdom and lack of vision, start using the same variable to mean different things.
Awesome.
Last week, capital M meant what? Molarity. This week, capital M means molar mass of a gas. And we're going to calculate it from the density of a gas. And the next lab that you're going to do, I already have it planned. We're going to do it before we take the midterm exam. I'm going to give you a gas. You're going to calculate its molar mass from doing some measurements. The measurements are going to be density measurements. All right? Okay. Density is a property that can help identify material. And the reason why is because it's independent on the amount of sample of a substance that you have. I can have like a small amount of gas or a big amount of gas, and the density of that gas is going to be the same, provided I don't change the pressure or the temperature on that gas. Density tells you how tightly packed particles are, right? So it shouldn't change. And density is also unique for every substance. The density of water is going to be different than the density of nitrogen. Right? You're welcome. The reason why the density of water is greater than the density of nitrogen is because water hydrogen bonds. And so the particles stick to one another, whereas nitrogen is nonpolar. It doesn't stick to one another. Like the nitrogen particles in a container won't really stick to one another very effectively because London forces are very weak. And so those particles will basically escape from one another's pull. So they won't pack very tightly. So you can definitely use density to identify material. It's kind of a very useful first thing to use to identify material because it's easy to measure. All you need to do is have a scale to record the mass of a substance, and you have to be able to figure out the volume of that material. If it's a regularly shaped solid, you could figure out the volume by using a ruler. And if it's not a regularly shaped solid, you could use water displacement. to figure out its volume. It's really pretty easy stuff to do in the lab. So when you measure the density, let me tell you the punchline first, and then we'll do some problems. Say, for instance, I measure the density of a gas, and I want to identify it. The way that you identify it is you do some calculations to calculate its molar mass. And I'm going to show you the formula that you're going to use in just a moment. For example, say I have a gas, and the measured density of a colorless flammable gas results in a molar mass, that's a big cursive M, equal to 2 grams per mole. Well, what is that gas? It's only one choice. It's only one gas that can be that light. What is it? It can't be helium. Helium is 4 grams per mole. Hydrogen. Why 2? Why isn't it 1? Because it's diatomic. What if I have another sample of a different gas and I measure its density and I calculate its molar mass and I find that it has a molar mass closer to 32? It could potentially be oxygen. Could it be an organic substance? Where? Of a colorless flammable gas. Could it be an organic substance with a molar mass? Like, could you have like a combination of carbons? So that's 24, 25, 26, 27, 28, 29, 30. Could it be ethane? Maybe. 2 grams, you could account for percent error. It could be ethane. Could it be ethanol? No, ethanol would be too heavy. Okay, but it could be something else. But your choices of what it could be are limited now, right? Because there's only it could have bromine in it. Bromine's too heavy of an atom, right, for it to be 32. So it helps limit your choices as to what that identity could be. All right, and you would do other follow-up experiments to double check what that substance is. All right, percent composition experiments or combustion experiments, whatever. All right. And so, here's the second example that I just gave verbally. You could write it down. So say you have a second sample of a gas, also colorless and flammable, that yields a density that allows you to calculate the molar mass to be 32 grams per mole. What could it be? Maybe it could be oxygen. Yeah. Methanol does work. Could be methanol. I haven't taught that. No. Positive. You want to really know? Molarities, moles per liter, molalities, moles per kilogram solvent. Molarities, moles per liter solution. We're never going to have to do molality. Because you use molality for colligative properties, for freezing point depression and boiling point elevation. It's not part of the AP program. You probably learned that in IB, right? Molality. Yeah, we don't do that in IB. All right. Okay, so I say oxygen. Maybe it could be ethane. Connor says, no, that's not good enough because 30 grams per mole is not close enough to 32. He says methanol, right? What's the formula for methanol? And an OH. Well, let's see how much does that weigh. That's a 12 plus a 16 plus 4. Oh, 32. Could be that. You would do a follow-up experiment to pin it down. All right? I could burn it. See how much carbon dioxide and water I make. And do a combustion analysis type question. Right? If I take O2 and I try to burn it, will I make any carbon dioxide? Okay. You could look at its state at room temperature. Methanol. What state is it in at room temperature? It's an alcohol. It's a liquid. Versus this sucker that's a true gas. That's gaseous as well. Okay. So those you can't just look at one piece of evidence, is what I'm saying. You'd have to do you have to look at a couple of pieces of evidence to help you pinpoint exactly what substance you're playing with. But the experiments, in any which case, are really easy to do. Picking up a container and looking at it is an easy thing to do. Is it a liquid? Is it a gas? Right? Doing a density calculation or doing a density experiment is easy to do as well. Certainly within your reach. All right. How do we calculate molar mass from density? Well, the way that you do it, we could write this down. I don't think it's all that necessary, but so, like for instance, if you know that density is mass over volume, right? You could take the density formula and rearrange it solving for mass. So what's mass equal to? Density times volume. All right. Molar mass. What are the units for molar mass? Like when I calculate molar mass off the periodic table, what are the units for that? Grams per mole. You could rewrite the equation as big cursive M, molar mass is equal to M over N. So little m being mass, n being moles. And again, I could solve for little m. And now I've got two equations that are basically solved for the same thing, right? Little m. And I could set dV equal to capital M times N. All that, I need stuff needs to be separated. Okay. It's true, Connor.
Is that big M?
No, it's a big... I'm trying to make it cursive just to differentiate it from molarity. It's not a mu. All right. Do you want scissors? All right, now, we're going to do this experiment next week. You're going to use this equation. The density of a gas you can measure directly. The volume of a gas you can measure directly. The number of moles of a gas you can measure directly. I've got the instrumentation to do that. So if you can measure this, this, and this, it'll give you the molar mass. All right? Actually, you don't measure the number of moles directly. You measure them indirectly. And where would we get N from? You would get N from the ideal gas law. All right? The pressure, the volume, the temperature I can measure. I've got thermometers, I've got pressure sensors, I can measure volume with a cylinder. And you can calculate indirectly, you substitute it in here, and then that allows you to figure out for molar mass. So these are all measurements I can make. Ultimately, for you to be able to calculate molar mass, it's about taking that density formula and the ideal gas law formula and combining the two equations together into one equation. And that's on the back of this sheet. If you don't understand this derivation, I don't really care. You don't have to understand the derivation. What you do have to know is the final master equation, which is here. And here's the derivation anyways. Okay? So if you take dV equals mn, and then, so you solve the ideal gas law for n, and you substitute PV over RTN for n, you end up with this monstrosity. And if you take that equation and solve it for capital M, you end up with this equation. All right? And you could, again, write that whole derivation down if you really care to. Completely unnecessary. Know this. So the final equation that you're going to need for the problems that we're going to do next is M equals dRT over P. And I'm going to do one or two problems and then I'm quitting. All right, we're going to go measure our filters and then we're done. So I guess you're going to have to do some problems tonight. But these questions are quick. Okay.
Is it both things you do on this?
Mm-hmm. You got 2 days. All right. That capital M stands for molar mass. D stands for density of the gas. Again, we have R. What's R? 0.0821. T stands for temperature in Kelvin. P stands for pressure in atmospheres. All right, so let's take a look at a question like 10.7 in the book. Now, this formula is not on the reference sheet. So that might be one that you're going to have to memorize flat out. Or you can sit and try to derive it. Yeah, it's not on here. You can try to derive it from the equations that they give you. All right. Okay, so let's take a look at 10.7. There it is. 10.7 asks, what's the density of carbon tetrachloride at 714 torr and 125 degrees Celsius? All right, so let's take a look at how we do this. What's the only formula that you've had in this chapter that has density as a variable? That one right there. Okay? All right, so this is how you do it. Well, what's the formula for carbon tetrachloride? CCl4. All right, so we've got this formula to play with. They want D. If you rearrange the equation solving for D, it ends up being MP over RT, right? So that means that somehow from the word problem, you're going to have to be able to figure out the molar mass, the pressure, R, and T. All right? Did they give me the pressure in the question? They did. It was 714 torr. What's the problem with that? Not atmospheres, so you change it to atmospheres. How about R? Do I know what R is? Yeah, it's memorized. What about T? Did they give me T? What's the problem with that T, though? Not in Kelvin. So you add 273, change it to Kelvin. What about M, molar mass? Oh, but I know it's carbon tetrachloride. What's the formula for carbon tetrachloride? CCl4. How do you get molar mass if you know the formula for something? You just look at the periodic table. You take the mass of one carbon plus 4 chlorines. And it ends up being 154 grams per mole. It's just a matter of taking these numbers in the correct units, shoving them into that formula, solving for D. So what do you get for D? 4.43 grams per liter.
We're done.
No, one more question. Uno más. Okay, straight up plugging and chugging. All right. Uno más. Oh, yeah, let's not do 10.8. It's ugly. Let's stop there. If we need to, we can do 10.8 when I see you next time. We've been long enough at this. Okay? All right, so